Hi, I'm Rob. Welcome to Math Antics. In our video about basic linear functions, we learned that the equation y equals mx plus b can be used to represent any linear function on the 2D coordinate plane. In this video, we're going to dive a little deeper and learn two new equations, one for calculating the slope of any line, and the other for calculating the distance between any 2 points on a line. To do that, the first thing we need is 2 points. 2 points! Actually, I meant 2 points on the coordinate plane, but nice shot anyway. We're going to name these points point 1 and point 2. As you know from geometry, a line can be defined by any 2 points. All you need to do is connect the dots to get a line segment. And you can get the infinite line by extending that line segment in either direction. Our goal in this video is to learn how to find the slope of a line segment like this and to calculate the distance between its 2 endpoints. The key to accomplishing those goals is to realize that you can use any line segment to make a right triangle. To do that, start from the point that is the highest on the coordinate plane and draw a vertical line straight down towards the bottom of the coordinate plane. Next, move to the other point and draw a horizontal line until it intersects the vertical line you just drew. See? Now you have a right triangle. The vertical and horizontal sides of the right triangle are perpendicular to each other, so they form a right angle. And the original diagonal line segment is now the hypotenuse of the new triangle. Temporarily, we're going to call the horizontal side of the triangle change in x and the vertical side change in y, which are awkwardly long names, but that's exactly what the two sides represent. Imagine starting at point 1 and then slowly moving along our line segment towards point 2. As you do that, the x and y coordinates that you're located at are changing, right? Your x coordinate is changing because you're traveling to the right, and your y coordinate is changing because you're traveling up. And when you finally get to point 2, the total change in your x coordinate would be the length of the horizontal side of the triangle, and the total change in your y coordinate would be the length of the vertical side of the triangle. That's cool, but the names change in x and change in y are kinda long. Fortunately, mathematicians have a shorter way of saying the same thing. They use the Greek letter delta as an abbreviation for the words change in. That means you can just write or say delta x to mean the change in x, and delta y to mean the change in y. Okay, now that we know what those sides represent and we've got nice names for them, how do we actually calculate the lengths of those sides? To do that, we just need the coordinates of the 2 points that form our line. Since we named them point 1 and point 2, it makes sense for us to call their coordinate values x1 and y1 for point 1, and x2 and y2 for point 2. We write the 1s and 2s as subscripts after the variables so we don't mistakenly think it means x times 1 or x times 2. The subscript numbers are simply a way of distinguishing the different variables in the problem so we can keep track of which is which. Anyway, to calculate the delta x, you need to find the difference between the x coordinates of the 2 points. In other words, you need to subtract the x value of the first point from the x value of the second point. So, delta x equals x2 minus x1. Likewise, to calculate delta y, you need to find the difference between the y coordinates of the 2 points. So, delta y equals y2 minus y1. These simple equations for finding delta x and delta y are important because they're used in the equations for slope and distance, which is what I want to show you now. The equation for the slope of a line looks like this. Slope equals delta y over delta x. Remember that the fraction line means division, so delta y over delta x is the same as delta y divided by delta x. You might also see the slope equation written in expanded form like this. The only difference is that the delta x and delta y have been written out to show the subtractions you need to do to get those values from the coordinates. Either way you want to write it is fine. And some of you may have heard this same equation expressed using different terminology. Have you ever heard someone say that slope equals rise over run? Rise and run are just different names that are sometimes used to describe the change in y and the change in x. The idea is that if you were to run along the line in the x direction, you would rise by a certain amount while you did that. Or would you? What if the line has a negative slope, which means that as you move in the positive x direction, the y value decreases instead of increases? That would be like going downhill instead of uphill. And the word rise seems less fitting in that case. Because of that, we'll just use delta y over delta x in this video. But it's certainly not wrong to use the terms rise and run, especially if it helps you remember the formula. But if you do, just remember that the rise can also be negative. Now that you've seen the equation for slope, let's see the equation for calculating the distance between 2 points on the line. Distance equals the square root of delta x squared plus delta y squared. Does this equation remind you of anything you may have seen before? It certainly reminds me of something I've seen before. You stole my theorem. Hi there, Pythagoras. I didn't steal your theorem. I'm just borrowing it so I can calculate some stuff. Don't worry, I'll give you credit for it. Oh, well, I guess as long as you give me credit. Do you remember how the Pythagorean theorem tells us the relationship between the three sides of any right triangle? That means that if you know the lengths of two of the sides, you can calculate the length of the third side. Well, we just saw that if you turn a line segment into a right triangle, you can calculate the lengths of two sides, which would be delta x and delta y, right? So we can just plug those values into the Pythagorean theorem. You're used to seeing that theorem in this form. A squared plus b squared equals c squared. Since a and b are the lengths of the horizontal and vertical sides, we can plug in delta x and delta y instead. And instead of c squared for the hypotenuse side, let's use d squared because the length of the hypotenuse equals the distance between our 2 points. To solve for d, or distance, we take the square root of both sides and we get d equals the square root of delta x squared plus delta y squared. This special form of the Pythagorean theorem is usually called the distance formula in algebra because you can use it to find the distance between any 2 points on the coordinate plane. And just like with the slope equation, you'll often see it in expanded form, where the delta x and delta y are written out as the subtractions x2 minus x1 and y2 minus y1. Alright, now that we have our equations for slope and distance, let's see them in action. Suppose we're given 2 coordinates, and we're asked to find the slope of the line they form, and the distance between those points on the coordinate plane. The first thing we need to do is name the coordinates, since they aren't named already. And even though it's not really necessary, if you're like me, you might want to draw a little sketch of the problem to help you visualize what's going on. The equations for slope and distance both use delta x and delta y, so let's calculate those values first. Delta x equals x2 minus x1. And in this problem, x2 equals 4, and x1 equals negative 2. So delta x equals 4 minus negative 2, which is just 6. Next we calculate delta y. Delta y equals y2 minus y1. And in this problem, y2 equals 3, and y1 equals 0. That means delta y equals 3 minus 0, which is just 3. Great, now we have our delta x and delta y values. And you can confirm that we got them correct by looking at our graph. The length of the delta x side is 6 units, and the length of the delta y side is 3 units. Now let's plug those delta values into the equations for slope and distance. Slope equals delta y over delta x. We just found that delta y equals 3 and delta x equals 6. So our slope equals 3 over 6, which simplifies to 1/2 or 0.5. That was easy. Now let's plug those deltas into our distance equation to see how far apart those points are. Doing that tells us that the distance equals the square root of 6 squared plus 3 squared. 6 squared equals 36, and 3 squared equals 9. 36 plus 9 equals 45. So the distance between the points would be the square root of 45. You could also simplify the answer to 3 root 5, or use a calculator to convert it to a decimal, which would be 6.708 rounded to 3 places. That wasn't so bad, was it? But let's try one more example to make sure you've got it. Again, we're given 2 points, but this time they're already shown on the coordinate plane for us. We'll label this one that's furthest to the left point 1 and the other one point 2. That means this point's coordinates will be x1 and y1, and this point's coordinates will be x2 and y2. First, we plug those coordinate values into the delta equations. Delta x equals x2 minus x1, which is 1 minus negative 3. So delta x equals 4. Delta y equals y2 minus y1, which is negative 2 minus 5. So delta y equals negative 7. Again, we see that those delta values agree with the graph and the right triangle formed by the line between the 2 points. Or do they? One of our deltas is negative, but a length can't be negative, can it? Well, no, but remember that deltas are really a difference between coordinate values, so they can be negative. The lengths of the triangle's sides are really the absolute values of the deltas. But the signs of the deltas are important because they help us get the correct slope, since a slope can be positive or negative. Now that we have the deltas, let's plug them into our equation for slope. Slope equals delta y over delta x, which would be -7/4. We could just leave the slope like that as an improper fraction, but we could also convert it into a mixed number form or get the decimal value with a calculator, which is -1.75. Now that we found the slope, let's find the distance between the points by plugging the deltas we already calculated into that equation. That gives us distance equals the square root of 4 squared plus -7 squared. 4 squared equals 16, and -7 squared equals 49. That means the distance is the square root of 16 plus 49, or the square root of 65. That root can't be simplified, but we can use a calculator to convert it to a decimal if we want to, giving us a distance of 8.062 rounded to 3 decimal places. Alright, so now you know how to calculate the slope of a line if you know any 2 points along that line. You also know how to calculate the distance between any 2 points on a line using the so-called distance formula, also known as the Pythagorean theorem, invented by me, Pythagoras. Ah, yes. Thank you for reminding us, Pythagoras. Remember, the key to success in math is to practice, so be sure to try some slope and distance problems on your own. As always, thanks for watching Mathantics, and I'll see you next time. Learn more at mathantics.com.